All right, Chapter 12, Section 3, Proving Triangle Congruence by SAS. This is going to be the first of several acronyms that we use, little letter abbreviations of a theorem that we're going to use commonly. So SAS is just an abbreviation for side, angle, side. And so this is going to be the start of how can I show two triangles are congruent without having to go through what section 2 describes as basically going through all three angles and all three side lengths without having to go through each of those measurements to show that they're the same as another triangle before I can reach the conclusion that they're congruent. Basically, section 3 and section 4 and 5, what we're going to move into throughout the rest of this unit is what's the minimum amount of information I can have so that I can show that both triangles are congruent, which means that everything else has to also be correspondingly congruent. Okay, and so let me clarify that with this example. So here we're shown side, angle, side, and this is the formalized wording, the formalized definition of what side, angle, side theorem says. If two sides and the included angle, I'll describe what that means in a second. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles have to be congruent. Basically, if I can show that two sides and an included angle between two different triangles are congruent, then that's not all the information, but that's a minimum amount of information that I can show that everything else must also be congruent to everything else in the two triangles. So the main focus here, the main confusing point is this term right here, included angle. What is an included angle? Basically, it's the angle that's sandwiched between two sides. So for instance, in this case, here I have angle B sandwiched between side AB and side BC. Angle B is the included angle of those two sides. Basically, it's what makes that wedge. Okay. Angle C would be the included angle of these two sides. Angle A would be the included angle for these two sides. So that's what included angle means. Over here, this is an example of something I could not use, okay? Because each of these angles are not what we would call included angles. See how I have side, side, and then angle? Okay, that order matters there, that SAS. Yes, unfortunately, we do not have a math theorem called ASS. As great as that would be, there is no AS theorem. I apologize. Math is boring even at that level. So back to this, why does this not work? It's because this is not an included angle. It's not wedged in between the two sides we're talking about. Okay, and all of that is to say is that in order to use this theorem, these features have to be true. Two sides congruent to two other sides in another triangle, and the angle that's wedged in between those two sides has to match. Why? Because technically, I can create a scenario where I have these features true between two triangles, but they're not congruent. Okay? As soon as the angle is wedged in between the two sides we're talking about, as soon as it's an included angle, then that's going to lock everything else into place. It locks everything else into place. And here's again the value of this theorem. If I can use SAS to show like, all right, well, I have two sides, included angle, two sides, included angle, great. The two triangles are congruent. That saves me half the work because now I can say like, all right, well, because these two triangles are congruent, angle C has to match angle F. Side AC has to match side FD. Okay, so it saves us some work. It basically cuts the work in half of what section 2 required. In section 2, if I had to show that two triangles were congruent, I'd have to show that all three of the angles were congruent to each other, and all three sides were correspondingly congruent to each other. That's a lot of work. That's 6 pieces of information to solve for. With side, angle, side, that cuts that down to only 3 pieces. Okay. But again, the confusing part, the tricky part with this is that it's the included angle. It has to be the angle wedged between the two sides in question. Okay, but I need those 3 pieces of information. So what will that look like in example form? Just going to go ahead and jump to whiteboard at this point. We're going to start with a proof. This is a callback to some of the stuff that we did in a previous chapter on reasoning and proof. We will be revisiting these, particularly for proving using these theorems that two triangles have to be congruent to each other. And then we'll deal with this guy involving inscribing this stuff in a circle. So let's jump to our whiteboard and do our two examples for section 3. Dealing with side angle side theorem. How can I show two triangles are congruent with minimal information? So our first example is a proof. And just reminding you in my course what you will see, what you're going to see on your big ideas assignment. Most of them will have some sort of fill in the blank scenario. So there'll be some pieces filled in. You have to fill in the missing chunks. Others will have little drop down menus like on big ideas where it'll have like a drop down menu here with different reasons as to why this claim is true, or different claims as to what matches with that given reason. That sort of thing. That's what you'll be seeing. But on my tests, what you might see at the end of your final, it will be this kind of format here. So fill in the blank. I give you some of the structure. You have to find the missing piece. So in this example, we're given a diagram. We're given this parallelogram kind of looking thing. You may not know what that is yet, but we have this figure and we're told this information. Segment BC is congruent to DA. That's what these little dash marks here mean. Okay, so that segment is going to be the same length as that segment, whatever that length is. And then we're also told those same two segments are, here's that symbol for parallel. They're parallel to each other. So that's an interesting thing to include in given information. I'll talk about the significance of that in just a minute. But you'll notice that with these red arrows, which you may recognize from previous chapters. Chapter 10 in particular, we talked about parallel and perpendicular lines, and we dealt a lot with those arrows from that unit. So we're given this diagram, that given information, which is again expressed there in red. We're asked to prove that triangle ABC is congruent to triangle CDA based on this information alone and this diagram. So ABC is this top triangle. CDA is this bottom triangle. Based on this information, I want to show that this triangle is congruent to that triangle. Okay, so we're given a bit of a structure, and as you get more and more experience with this in higher level maths, this will just end up being blank. You'll have some given information, you have to reach this conclusion. So here's the automatic point for everybody, and that's that the very first step in any proof, the very first claim that I can have is just my given information. Basically, what do I see on my diagram and what information was I told? So this here is where I would have segment BC is congruent to segment DA, and the same segment BC is also parallel to that same segment DA. Where did that come from? That's just a copy and paste from up here. What's my reason for why that's true? It's given. I can only start any argument with whatever I have to be given. I can't speculate on anything, basically. Okay, so something in this is going to lead me to this second claim. Okay, now just as a little spoiler alert to bring us back to what this entire section is about, it's the side angle side theorem. So the spoiler alert here is I'm probably going to use side angle side within this proof to show ultimately that these two triangles are congruent to each other. So I want a side, another side, and the angle that's included or wedged in between those two sides to be congruent between the two. So I already have a side. Okay, I have one side congruent to another side. So I need another side, another pair of sides to be congruent, and an included angle. That's kind of the end goal here. So in my second step, I give you this information. Here's a claim. Angle BCA, so it's this little wedge guy in there, is congruent to angle DAC. DAC is this little angle right in there. And so this is the next claim. Well, there's my angle. But why is that true? This actually goes back to this piece of information here. Because BC is parallel to DA, shown by these red arrows, this has to be true. And this is a callback to chapter 10. Why do these angles have to be true? The name of this is the alternate, I'm going to abbreviate, alternate interior angles theorem. Alternate interior angles theorem. Why can I use that? Because I have parallel lines or parallel segments. In chapter 10, if ever I had two segments or lines that were cut by a transversal, so here are my two parallel lines. My transversal is this AC. And so according to alternate interior angles theorem, my opposite inside angles, basically what makes a Z, those have to be congruent. So this is a result of this, BC being parallel to DA, and that's from chapter 10. So if this helps just to kind of, where did this come from? Why can I use this? It's because BC was parallel to DA. Technically, I don't need this piece here. That's just the reasoning why and the justification as to why I can use this theorem. But technically speaking, I can just write this theorem. This is just why I can use it. All right, so now I have a side and I have an angle. I need another side. Well, here's in my step 3, here's that other side. So I'm going to have side, angle, side. And it doesn't have to go in that order. What has to be true is I'm going to have a side, and I'm going to talk about this side in a second. It has to be the angle wedged in between the two. I'll clarify that in a minute. But AC is congruent to AC, and this seems like a very dumb thing to say. Obviously, something is congruent to itself. Obviously. But why did I take the time to say that? AC is congruent to itself. There's a stupid property that makes that true, and we call that stupid property the reflexive property. This is one of the foundational properties of all of mathematics, and it basically says this: any object is congruent to itself. So if I were to take this expo marker and measure all of the things around it, well, they would equal the measures I took all the way around it. It's a very stupid property, but what it also means is that I have a side congruent to itself. Why did I take the time to do that? Because both these triangles share that same side, which means that is a side congruent to another side in a triangle. So here, just to show what we've just done with these 3 claims, BC and AD are congruent. AC, in this last one, we proved is congruent to itself. There's 2 sides in both these triangles that are congruent to each other. The included angle, so I had side AD and AC. The included angle is the angle that's wedged in between them. There's DAC, this guy. And in this other triangle, BC and AC, again, the angle wedged in between is this guy, BCA, which is that one. What we've shown is that 2 sides and their included angle are congruent to each other between 2 triangles, meaning that by side angle side theorem, these 2 triangles have to be congruent to each other. Okay, so just based on that information, we were able to reach this conclusion using side angle side. All right, let's try and do our last example here really quickly. Here we're given this diagram. Now I have a circle, and I have this series of triangles, not series, but 2 triangles drawn inside. And I'm told QS and RP pass through the center M. That's an important thing to state, because we're going to use something you've actually heard in a previous math class before, that if QS passes through the center of the circle, that has a name. That's a special type of segment. It's what we call a diameter of this circle. QS is a diameter. RP is also a diameter. Why? Because it passes through the center M. Why does that matter? Because in a circle, the diameters have to be congruent to each other, but also the radii. Each radius from M to P, from M to S, from M to R, from M to Q, all have to be congruent to each other, meaning each of these sides has to be congruent to each other. Why does that matter? I need to prove why MRS and MPQ, basically this left triangle, is congruent to that one. Well, now I have 2 sides congruent to 2 sides of the other. I just need to show the included angle wedged in between those sides is congruent. Basically, I need to show this. Why? I'm just going to jump right to that conclusion. These are what we call vertical angles. Vertical angles is if I make an X, opposite angles have to be congruent. side, angle, side.